we're going to play some music here because this is a professional show. And then we're going to jump into assembly language, part 8 in the ongoing series, hosted by Mr. Steve Bjork himself. So cue Rock Tune by L. Curtis Boyle. Frickin' piece of crap, frickin' soundboard. What a shit show this is, huh? All right, let's try this one more time. So look at this every single time. The only reason why I don't smash this is because it's $160. And so if it was a cheap piece of crap, I would have rage smashed it a long time ago. Let's try this again. Take it away, Steve Bjork.
Okay, today we're going to continue a little bit about how you can change the order the instructions are run. Last time we talked about branch and branch based on conditions, and if a number was greater than or less than, how we can change the order. Now we're going to talk about jumping and calling subroutines. So let's go to the next slide. All right. As I said, in lesson 7, we talked about branching. That was used to make decisions and like that. And we're going to now talk about the first non-branch. It's called jump. And this is similar like basic, where you got to go to. You're going to go off to a line number. Well, in the case of the jump, you could sit there and say jump to 8,300 ED, that's an hexadecimal, and it'll jump to that location. Unlike those branches that we talked about in last week's episode, those were basically always branching kind of around itself. In other words, jump 20 ahead, jump 30 back, stuff like that. And that made it very nice if you moved the program. It could always stay within itself. This is one of the things that's key, as Curtis knows, with OS 9. Everything's got to be relative because you never know where you're running in memory. Well, sometimes you got to refer to things that are an absolute. Like, for example, if we jump to the example that we have here of 83 ED, that would be someplace in the ROM. I just came up with a random number there, but I don't know what it does at that particular location. But even if you move the program, it is going to jump to that particular location. It's very handy to make sure that you know where you're going and what you're getting. And jump also has a lot more options in it too. And why don't we go to the next slide? As I said, the jump can be used to go to a new location. One of the things that you can do is actually have it where the jump is more like an on go to. In other words, in BASIC, an on go to, you've got a list of different addresses you're jumping to. Well, you can do the same thing in assembly language. First, what you do is you load up one of the index registers with the address of the table that contains all the different addresses. Then you load up, let's say, one of the 8-bit registers with a offset. This is how far that we go into the table. And then the jump is able to actually go out there, look at where that table is, look how much you're indexing or skipping through the table, grab the address, and jump to. But let's take a look at how that actually works in assembly by going to the next slide. Okay, up at the top here, we've got something you've never seen before. This is a data statement. The DW stands for data word. It means that we're doing 16-bit values, 2 bytes for every location, and that contains the address somewhere that we might point to in memory. So address 0, address 1, address 2 are the addresses that we've stored in our table, so we can refer to it. So our first instruction in the actual code that's going to do this on go to is load X with where in memory is this table. That's what the #J table does, loads up the address. Then we load up the B register. Remember, that was an 8-bit register. We load that up with the jump number. we try and figure out which one of these addresses we want to use. And of course, in assembly, one thing we do, we don't start counting with 1, we start counting with 0. 0 is always the first item, 1 is the second item, and 2 is the third item, etc. up. So you'll have to get used to that. Instead of like basic, you do a step from 1 to 10. Assembly language likes to do a step 0 to 9. So since this table contains 16 bits of address information in each of those addresses, what we have to do is multiply what we just loaded into the B register by 2, so that we can now point to words instead of bytes, since a word is every other byte. And we, of course, use the logically shift to the left B to multiply that register by 2. So once again, you see how easy in the earlier lessons we talked about shifting, how shifting is used to do multiplication. And you're going to do a lot of that in assembly, taking things that are normally referring to bytes and you want to refer to words, or you want to refer to something else. Now we're getting into the actual instruction jump, and then we have a bracket, B comma X close bracket. Well, the B comma X means take where X is pointing, add B to it as the new location. So B, if it was 0 and we multiply by 0, we still get 0. You would actually add 0 to X to figure the thing out. Now, X doesn't change in this instruction. After we're done, it will still remain the same. But we will have a reference that we're looking at the first element. Now, if we wanted to look at the second address in the table, B would have been a 1. We multiply that, it becomes a 2, and it becomes the second word of the table, and that's B comma X. So we're basically emulating the on go to instruction here with this type of operation. So before, with the branches that we talked about last week, we were always talking about jumping to some location, and it was always like, if the answer was 0, we're going to branch there, or if we're going to branch always there. It was always about going to some location. The jump instruction, because it allows you to use all the different 6809 addressing modes, allows you to come up with unique and interesting ways how to calculate where to jump. And that's effectively what we're doing, is we're actually doing a calculation to figure out where in the table we want to pull up the information. So this would be handy if, for example, let's say that you had a COCO 1, a COCO 2, and a COCO 3. Well, address 0 would be something for the COCO 1. Address 1 would be for something for the COCO 2, and the third one would be address for the COCO 3. So we could have jump number actually be what type of COCO are we, and that would allow us to decide where to go to. So we can make our programs vary based on what we're looking at as far as information.
So that would be kind of an example of on COCO,
Yep.
go to, and then depending on the type of COCO
Exactly.
you have.
So,
and you could do stuff like tables. Like I say, you're moving your spaceship in Space Invaders. You could have offset address 0 go to move left, and address 1 goes to move right, or something like that too. So,
and this would get very handy with graphics, because you might have different graphic routines depending on the object that you're moving or drawing, or whether or not the object is dead center on the screen, or, somewhere within the window. And sometimes we have to use slower routines for clipping. This is where the graphic has gone beyond the edge of the screen. Because the way COCO's memory is working is, if you draw beyond the right-hand side of the screen, it's going to wrap on the left-hand side.
Yeah.
You've seen that a few times there, Steve. So this is used for making decisions in a different way. Instead of basically just taking a look at whether or not a number is zero or not, you're doing a jump based on a more elaborate calculation. So this is, as you can see, it becomes a function where this type of jump, where it uses the addressing modes, gets more elaborate. So yeah.
Yeah.
So every type of these type of instructions have situations where they really can extend the power of what you're doing in assembly. By the way, this type of thing where we look into a table, grab information out of it, and use that to jump somewhere, this is called indirect addressing, opposed to direct addressing. It's just a term that they use for saying we're going into something. Now,
so it's like a relative versus
yeah,
absolute.
well, even more so in the fact that we're diving into data. Now, I'm going to save you a little bit, Steve, because next week, that's when we're really going to get into all the different addressing modes that not only the jump can use, but when you load up information, when you're doing other things with the 6809. That one there, we might raise the death count a little bit, but I decided to take it easy on you and not talk about the different addressing modes that are available in the Coco. And trust me, Curtis is over there chomping out the bit saying, I love next week's episode.
Yeah.
I say we do it now.
Yeah,
we'll call it the meltdown episode, I think.
Yeah. Well, Curtis and I will try and go easy on you, Steve, next week for that one. But anyways, why don't we go to the next slide? Because we are going to talk about a few more things. Now, this slide really just reiterates what I'm saying is there are other addressing modes, and we're going to handle that in a later session. So, but yeah, let's go to this one. Much like good old BASIC, we have GOSUBs, and this is used to save from writing code over and over again. If you come up with a routine, a little bit of code that you like using a lot in BASIC, you make it a subroutine and you call it. So you don't have to have it all over your program. It's a great way to save space. And of course, assembly language has it too. And there's 3 basic instructions for that in assembly language: branch to subroutine, long branch to subroutine, and jump to subroutine. And why don't we go to the next slide and we'll do the first.
There are no arithmetic branch to subroutines. So.
Oh, in my code, there definitely is.
All right, so here's our BSR, branch to
It's
subroutine.
very much like the branch always instruction that we've talked about before. The instruction consists of a command and 1 byte. The byte is how far backwards and forwards to go from this instruction to find that call, that subroutine that you want to jump to. So its range is a -126 to a positive 129 from the instruction. Now, when you get to that subroutine, you have to know, hey, I got to come back. I'm done. I have to come back to whoever called me. That is done with an RTS. That's return from subroutine to get back. So that's kind of like the return in BASIC. Very simple.
GOSUB return.
Yeah. And the example I show at the very bottom of the slide, sorry, it's almost off the screen there, BSR time delay. This is like, I wrote some code that does a short time delay. I use it quite a bit. So I call it, it goes off and does it and comes back, just like BASIC. There are some gotchas. We'll go over those in a few moments, but let's go to the next slide. All right. Well, as I said, the last instruction was limited in range. You could only do a subroutine that was pretty close. The long branch to subroutine has the entire range of memory. In other words, it's very much similar to the long branch instruction, long branch always. It will go off to the subroutine, and it can be more than that -126, 129 range. It can be thousands of bytes somewhere else.
Anywhere in 64K.
Exactly. So it gives you the full range. It's very simple. It does the same thing where you get to the routine. When you're done with at the routine, you do an RTS, and it will come back and start executing the program, just like the way the GOSUB works in BASIC, and goes off and does the code and continues down after the GOSUB. So works the same way. Let's go to the next slide. Let's keep moving through these. Don't want to take too long. All right. Jump to subroutine is one where you've got lots of different addressing modes, like what we had with the old jump instruction where you're jumping to a location, and it goes off, you do the call, and it comes back with that same same return from subroutine operation. I've got an example here where you do a JSR, and it's got that fancy brackets again for indirect, $A000. This is the routine that calls the character read from the keyboard that's in the ROM. And actually what's stashed at A0000, A3 zeros, is the location in the ROM that actually has the routine. So by jumping this location, no matter how the ROM is changed by the different people that worked on it, it knows where to jump. Basically, it's just an example that I'm using where you can see with the JSR, you can do a lot more than just simply jump to a location. You can do other things. And all that type of different addressing we'll cover in next week's lesson.
Yeah, and this is an excellent example too of why you have absolute and relative versions. Like the branches, like if you want to relocate your program and move it around, it'll follow where you're going, but your ROMs don't move generally. So in this case, you want to, no matter where your program loads, you want it to jump to that exact location where the polecat routine, in this case, the pole keyboard routine is, and that doesn't move. So that you would use an absolute JSR rather than a BSR.
Exactly, and you know, they definitely had that foresight when they're designing the 6809 as far as getting that in there. Now, much like basic, subroutine calls can be nested. In other words, a subroutine could call another subroutine, could call another subroutine, and they'll all know where back to go from when you hit that return instruction. Basic keeps track of who's calling from where and how to go back and like that. But in the case of the 6809, it does the same thing, but you've got to do more work. That's one thing you're going to learn about 6809. It's up to you to hoist that load and put it on your back and carry it with you. And the 6809 uses something called the stack or the stack register. All the BSRs, LBSRs, and JSRs place their return locations on the stack. And of course, the RTS simply removes that return location off the stack to go back. So the routine that you're calling, it don't care if it was a BSR, JSR, or LBSR as far as who called it, because they all do functionally the same thing of putting their return address on the stack, and then the RTS instruction, the return from subroutine instruction, pulls that information off the stack. So there's no confusion between those three different JSR or calling instructions. It all works out correctly, right? Right, Curtis?
Yeah, you don't need three versions of an RTS instruction. You can just use the same RTS for all three types, which makes it nice and easy.
I need like a 30-second decompressor. I've just heard so many, and I couldn't help but laugh. I didn't want to interrupt you, Steve, but I couldn't help by starting to think, well, is there an LGBTQ routine in there? There's just so many freaking abbreviations.
Is a long branch greater than or equal to
processor?
Yeah. Well, Stevie, I was trying to get to the DEFCON 4.
Oh, Christ.
And
so today,
also to prepare you for next week's lesson on the different addressing modes and the all too powerful load effective address instruction.
Okay, looks like Bruce Moore is raising his hand. Bruce, do you have a question?
Yeah, I do. I wonder for a description of what exactly a stack is, or a metaphor. Or something.
We're coming to that.
Oh, okay, perfect. Thank you.
Yeah.
Okay, Stevie, do you have any questions to kind of get a breather here?
No, I just needed to take a breath because I heard so many acronyms in one slide that my head almost did explode. So
I will try and say branch to subroutine instead of BSR. I don't want to pull a David Ladd on you.
Dry wire.
And yeah, no, because I do have a sinus condition right now. I do have a lot of pressure in my head, so there's not a lot of room for additional things to get in here. So.
But basically, the bottom
Okay.
line with this slide is to say that whether it's a branch from subroutine, a long branch from subroutine, or a jump from subroutine, the return doesn't matter. They all effectively take where they've got to come back to and stick it on the stack. And then they do, and then of course the return from subroutine instruction just simply says, oh, I'll take it off the stack. Oh, this is where I got to go. And it pops back there.
Yeah. It's just like basic where you have on GOSUB and you have a plain GOSUB. You just use the same return and command to come back. It doesn't matter which version of it called it.
Right. It's just like magic. It just knows it's going to return from wherever it was called.
But the thing is, and what I'm also alluding to in this slide a little bit, is you have to do some work with the stack. Anyways, let's go to the next slide.
Okay, we're moving on. Sorry about the interruption. I just needed a breather.
I was covering it rather quickly. Now, the stack in the 1609 is controlled by a register we haven't talked much about. It's called the S register. Boy, it's doesn't make it too hard to understand what the S for stack.
Huh?
Yeah. And the stack is used. It's built from the top and works its way down. In other words, it's pointing someplace in memory. And when you do some sort of BSR, branch to subroutine or long branch to subroutine or any of that stuff, it pushes something onto the stack. It literally goes downward. It goes from the high location to the location memory. Think of it as you're at a buffet and they got a bunch of plates. And somebody brings out new plates and they put it on the old ones and it pushes them all down. It's kind of like that. The way the stack works is whatever's on top, you're going to pull off the next time. And if you bring out new plates, you push them down onto that stack. So it's always kind of in this thing. It's like
it's kind of
very,
springy.
very springy. That's the way it works.
Okay.
So
and you've made me hungry too, so thank you. So
I want to mention one thing too. If somebody's coming from the 6502 or some other CPUs, they sometimes will refer to pulling off the stack as pop. Just terminology wise, I just wanted to explain that in case somebody has heard of a pop but doesn't know what a pull is.
Yeah.
So.
And by the way, this segment is brought to you by Golden Corral.
Yep, it's just like those stack of plates there. So,
all right.
But that's really, that's what's kind of unique or different. And stacks have been around for a long time on computers. They go back 50s or 60s, depending on who wrote the first stack in microcode. But it's really a powerful operation because look at the return. It doesn't know who called itself, but it does know, hey, I can just grab this off the stack and I can return back to where I'm at. So you don't, it cuts down on the confusion by using that.
And it cuts down on the programmer having to, do special things. Like if you're doing direct jumps back and forth like that, then you have to know, okay, well, where did I get called from? Like if you make a subroutine that can get called from 3 different places, you would have to keep track of which one called it. Do I have to come back to number 1 or number 2 or number 3?
Yeah, that could be mind.
Exactly. Yeah. And by the way, there were processors back in the early days that everybody seemed to want to come out with one where they actually had the bright idea they wouldn't put a stack register in.
Yeah, and I've worked on HP 3000 minis that were the opposite. Everything was stack based. They had no direct registers. Everything was on the stack. So you had to worry about, if you want to do the equivalent of a load A, you'd have to remember that A is always at, the second address on the stack or something like that, which I found confusing after using the 6809.
Okay. Anyways, about the middle of the slide, I talk about for the fact that when you want to push something on the stack, it effectively, you do a BSR. So it's got to put the return address of where to come back to on the stack. It effectively subtracts 2 from the stack and then writes 2 bytes to the stack of where this return address. Technically, that's not what it's doing, but effectively that's what's going on. Is it always subtracts from the stack when it puts the information on there.
Yeah. And maybe to clarify too, we should mention the stack, the S register itself is a pointer. It's a pointer to where the stack is in memory.
It's so an index register. It's an index register like the X register, the Y register that we've talked about before is just another index register. And by the way, on the stack, all those beautiful addressing modes that I keep alluding to work on the stack register. So yeah, that's why I keep on saying next week's episode, everybody's got to turn in because we're going to see how high we can raise Stevie's DEF CON level.
I might have to start coding between now and then just to get ready for this. So.
Anyways, okay. But that's basically when information gets put on the stack, it always subtracts first before it goes on there. By the way, when you pull information off the stack, as I said, it works its way up. It gets larger numbers. It grabs the information and then adds to itself. So it's the reversed order. That sound okay, Stevie?
I'm not sure if you just said that it increments or decrements itself, though.
It increments itself. It decrements when it saves information onto the stack. It increments when it takes it off.
Okay, so when you do a return, it just pulls a word from the stack, 16-bit value, and then it jumps down another 16 bits to the next value in the stack. So every time it returns, it goes to the next number in the queue, basically,
Exactly.
Kind of like a turnstile.
Or just like those plates. When you take a plate, all of a sudden another one pops up.
Another one pops up. Right.
That's exactly how it works.
All right.
Now, the thing is, you got to always make sure there is enough room for all that information you're putting on the stack. If you don't, you get buffer overrun errors. Where have we heard that before?
Microsoft.
Yeah.
Windows, DOS.
Mac, everybody has that problem.
Everybody. So this is what I said. Now, in the case of BASIC, it manages for you. But remember, there were some options in the clear command that allows you to set up more space for the stack.
Okay.
Well, you just have to sit there and say, when I build a buffer for my stack, I've got enough room.
Yeah, and make sure it doesn't, if you put it too small and you put it too near your program, you can actually start putting stuff on the stack and then start overwriting your own code, which can cause all kinds of problems.
Now, one trick that I used, this is just off on the side, a little note, not going to be a test on it. But one trick I would use when I'm developing my games back in the day is I would write some code through the buffer that I've set up for the stack, something unique like it would look like the @ sign if you displayed it on the screen or something. And then I would run my program. Then I would go back and I would verify how far all those little codes I had written in the buffer had been changed by the stack working. That way I could see, gee, am I almost out of stack space? Or do I have a lot more stack space and not have to worry about it? It's something that when we get into the more advanced programming elements, we're going to go over and talk about, setting up the stack buffer and making sure that you don't have any problems, because that's one thing that we definitely in this whole series is we want to point out where you can have issues so that you don't necessarily get into trouble. So why don't we go to the next slide?
Okay. We're moving on.
Okay, here's a simple little thing where we load the S register with the number 200. It's pointing to a stack buffer that I've set up that's from 100 hex to 1 FF hex, basically the second 256 bytes of RAM. I'm using the first 256 bytes of RAM for my direct page, which is a type of addressing mode we'll talk more about next week. Then I do a call, BSR to time delay, and it will put its information onto the stack at location 1FE and 1FF because they are 2 less than the 200 I had started with in the stuff. And then, of course, I do another call. So this is an example of a very large buffer, but it shows that I've set up my stack. And really, setting up the stack is not that hard. It's just setting aside space and then telling the CPU with the load S command where the stack buffer is going to be. It's not really that much magic. It's just maintenance you got to do. Right, Kurt?
All right, so that hex 200 basically says you're getting everything up to that value.
I'm saying that starting at basically less than 200 is where all the informations go. Because, like, for example, when I call the subroutine, the BSR in time delay, before the information is placed on the stack, what does it do? It subtracts 2 and writes the information. So it will actually go in 1 FE and 1 FF. It will not go into 200.
Right. How does it know to stop at 100?
It don't.
That's up to you.
That's when you get a over buffer run error. That's when your program starts messing up. And that's the thing, is you have to decide in your code how much space you need for stacking information.
Yeah. And BASIC does have that problem too. As Steve was mentioning, the clear command, you allocate how much space you want to use. And it defaults, 200 or something, if I remember. But if you do a whole bunch of nested subroutines and stuff like that, you can overflow basics too and have it crash with an error. So the same thing. I mean, there you would allocate more space if you're having problems, or string space. It allocated stuff on the stack for string space as well. And it's the same thing here. It's just a little bit more manual on your side. You don't have BASIC doing some of the stuff for you, but you do have to keep track of it yourself.
Okay.
Let's move on to the next slide. Okay. The stack can also be used to save and restore registers. These are the like the A and B registers, the X register, and stuff like that. This is very handy if you are going to call some subroutine that's going to change the B register, but you want to make sure that you have a copy of itself. Now, you could store it someplace off in memory, but you also have the option to push that information that's contained in the register onto the stack. And that is done with the push on system stack instruction, which is called PSHS. Boy, it's tough to say. But it basically copies the content of the register onto the stack. Now, the pull does the exact opposite. It pulls it off the stack and puts it into the register. So it's a way to remember, like those plates that we had at the restaurant. Let's say that you had a plate that you wanted to save for a little bit later. You just put it on that stack of plates, and then when you come back later, you can take it off. And so that's exactly what you're doing. You're putting it on there. And then you can pull it off. Now, the one thing is, you got to remember, you got to pull it off in the order that you push. And remember, the subroutines are also pushing on there too. So you don't want some idiot coming up in the buffet in between when you put the plate on that stack. Grab that plate off the stack before you come back. In other words, you're going to have to probably put a guard up there and make sure nobody takes your plate. In other words, you're going to have to keep track of it. So if you put information on the stack, you got to make sure you take the information off the stack in the order, and you got to be very careful about subroutines in the sense that you don't want to put something on the stack and have the subroutine try and pull the information off incorrectly, and then you pull it off. You can see there could be confusions. So you just got to be very guarded about how you put information on the stack and how you pull it off.
Yep.
Okay.
Curtis, you want to add something there?
I was just going to mention, like, for example, if you're calling a subroutine that's going to do some calculations, and let's say I need to use the X and the A and B registers to do this calculation, but when I come back from a subroutine, I want my answer in X only. I don't want A and B mucked around with. So you would do a push A, B, X. do your little fiddling calculations, and then you would do the pull, or you would pull D. Well, this is a bad, not the most optimal example, but I'd pull D off, and then I'd replace D with whatever the value that I was wanting to return with, and then pull X to actually get the X back to where it originally had started with. There's a few other ways to do it. You can modify stuff on the stack too, but basically you would use it to try to preserve things that you want to keep from the subroutine if you have to use a bunch of registers to do whatever that subroutine does.
I think our next slide will show a little bit more of what Curtis was talking about.
DEFCON 3.
Yeah. Hopefully it explains it better than I just did.
Okay. Let's say
It couldn't
we're
be
going to
any
go
worse.
back to that example we had before where we're loading up the X register and we're using the B register to go through and figure out which one of these addresses in our table to jump to. Well, let's say that the B and the X register we want to save from wherever we're coming from, because we're going to use them to figure out the jump. So the first thing we do in our instruction is we push onto the stack the X and B register. This saves them onto the stack. Now we load up X. Hey, it doesn't matter. We've saved it. We can now use X, load it up with a list of our subroutines that we want to jump to, load up the B register with our which one of the these particular jumps we want to do a call to, multiply B times 2 by doing a logical shift to the left B, and then we do a JSR indirect B comma of X, which basically goes off and calls our routine. So when we get there, what's been pushed onto the stack is where to come back to. That routine does its work. You do a return instruction, RTS, and then it comes back, and our last instruction is pull off the stack B comma X. It gets that information off the stack, and the B and X registers have been restored. They're back to what they used to be. So this is an example of how you can use the push and pull instructions to save information that you might be kind of destroying because you're doing some work here.
Right, you just have to be kind of calculated in the application of this, because anytime you do a GOSUB, you're pushing the stack down one plate. You want to make sure that when you return, you're right back to the same plate that you stored everything on.
Yeah,
right? You're not
exactly.
Okay.
So you
Gotcha.
know, they're very powerful. There's lots of tricks that we can do here. We're not going to show you those tricks, but the main thing is that this is how we can use the stack to temporarily store something, because the other way to store something is we could set aside variables in direct page to put information in. We could go through and there's other ways of doing it, but the stack gives us very easy temporary storage, and it also allows us to do recursive temporary storage. The recursive thing, as I said before, with when you do a GOSUB in BASIC, that can call another GOSUB, that calls another GOSUB. Well, this type of thing here, we're also doing kind of recursive data storing. We're saving this on the stack, and then when we come back later, we're able to get that same information. This is why you may have to have hundreds of bytes of data for your stack, because you've got so much information being pushed temporarily on the stack and then pulled off in the process of, let's say, a game, that you need that space. That makes sense there, Stevie?
Yep. I'm just getting hungry. Keep talking about plates and stacks. So.
I know.
Okay.
Okay. Let's go to the next slide.
We're moving on.
Now, the push instruction can save any or all the registers, including the condition code flag. And they're always pushed onto the stack in the same order. And I've listed an order here. Now, any or all of those registers can be pushed or pulled in one time. And that's the beauty of the 6809, is you list which particular registers. Like in the last example, I showed that we were pushing the B and the X. It knows the order of how to push them on the stack and pull them off the stack. So I don't have to think about that. But also, I could have added in pushing the Y register or pushing the A register. But all this stuff, they can be pushed. By the way, the PC, that's the program counter, and that's where the current instructions are being executed. And there are some tricks you can do with that. But these are the order that they get pushed and pulled off the stack. And to kind of see this a little better, let's go to the next slide. I've got a graphic for you to help kind of visualize a little bit better. Up at the top of all these different little squares, this is a representation of memory. And you see that FFFF, that's the highest point of memory. And down at the bottom, you got 0, 0, 0, 0. That's the bottom part of memory. And it shows how information is pushed on the stack, going from the top, working its way down, and then the same thing for pulling up the other way. And that's the order. It's simple. That's the way it works. It never changes the order.
And then one of the beauties of the 6809 is that you can push and pull multiple registers in one instruction. And a lot of the other 8-bit CPUs, you had to push each one individually. So you'd have to do a push A and a push X and a push Y type thing. And the 6809, you can just specify. And if you actually count the registers it's pushing or pulling, the maximum you can do is 8. So if you look at the actual instruction for push or pull, the second byte is the basically bit flags, and it's 1 bit per register. So CC is 1 bit, and A is 1 bit, and B is 1 bit. And you count that there's actually 8 registers that you can push and pull in a single instruction. And just to allude to something probably in a bit in the future here for advanced programming is that's the basis of stack blasting, that you can have one instruction.
That's what I was going to just cover.
Yeah.
Yeah, it basically, as you can see, there's multiple bytes being written and read at the same time. And that's why they use stack blasting to pull and push information into the computer's video memory a little faster than doing it a byte or two at a time. So
I'm sure Simon's very familiar with that.
Yeah. Anyways, now besides,
I just went to the next slide.
Perfect, because we need to move on. We don't want to hurt Stevie too much. Besides the system stack, there is also the user stack. This is a separate register. It's called U. Boy, they're so original with these names, aren't they? Anyways, the user stack works the same way as the system stack, but it's for pushing information that the user uses. It's a way to have a separate stack, separate from the system stack, where all these call to a subroutine get pushed. This one here could be separate data. So this is where you can have a buffer somewhere else in memory where you can push and pull information onto the stack and save it and like that. And by the way, OS 9 uses this extensively.
Yep. Right? Every single data area that every single program, including the system process, actually uses the user stack for pointing to where that is. Now somebody in the chat room is asking, why would you just, he was kind of get ahead of it, but he was going, why would you just not use the user stack at all times? And there's a few specific reasons. One I will just mention here, we're probably not going to get into it in much detail until later, is that IRQs are all based on the hardware stack. So if you're getting an IRQ from an RS-232 card or something like that, you want to be able to access a system stack to be able to figure out, where the data from the RS-232 port is, or, where the IRQ happened, that type of thing.
Yep. And by the way, this beginning of system stack, user stack, well, the user stack, only the user in later processors could access. The system stack was not allowed by user programs. And this is part of trying to make it so that computers are more secure. Because trust me, when they're developing the original processors, security was not an issue, not a concern. They didn't put much in there. This system and user stack that you see in the 6809 is the first inkling of trying to get some sort of security. In the 68000, there was more security. Later, 8086 based processors like the 386, 486 got more security. And they've been trying to write more security into the processors as we've been going along. So yeah. This is the beginning of a true computer processor.
And as far as I remember, the 609 was the very first CPU that had the user stack as a separate stack, correct? Like 652, they only had the system stack. So you always had to mix and match between your stuff and the CPU stuff.
Exactly. But anyways, this U register can be used for this user stack if you want, and it makes extensive use in OS9. I have to admit, in my video games, I never used it as a user stack. I used it as a regular 16-bit pointer, just like the X and Y registers. And it always pointed to my data structure, the particular object that I was working on. And that will definitely be something that will be coming up in later sessions of this series. But let's see. Let's go to the next slide.
Which I think is the last slide. Okay.
Now, we briefly touched on addressing modes with the jump and the jump to subroutine instructions. Next time, we're going to be covering the powerful 6809 addressing modes. And there's a lot of them, and they all make sense, and they're really powerful. And there's one instruction that goes with it that will make no sense at first, but it'll kind of like the light bulb will come on. It's called load effective address, the LEA instruction. And yes, definitely tune in next time to watch Stevie's head hit DEFCON 1.
Excellent.
I don't, the next one here, I'm sorry, it is going to get a little technical because there's lots of options, lots of addressing modes to go through.
Yeah, and it's also one of the reasons the 6809 was the most powerful 8-bit CPU.
Yep.
Change my mind. Right. So yeah.
And one thing, and the way they've set up the 6809, one of the things I've always said, with a lot of CPUs, it was a lot of work trying to figure out how to do something. The 6809 was the first one I ever used that had the aspect where there was multiple ways to do it. They just came up with lovely different way, and you just had to find the one that worked best for you in that situation.
Excellent. Excellent. Well, thank you for another great segment. Bruce, before I forget, and while you're still here, we do need to show off your latest Cocoa Forever teaser, right?
Sure.
Is there anything you need to use to talk this up, or we just play it and let it run?
It's just announcing another episode is ready to go. So.
All right. For those of you not aware of the Cocoa Forever project, we have here with us Bruce Moore, who's made that project, and he's got a brand new teaser for the latest episode. So let's run that real quick. Bruce is here. I didn't want to forget.
How does it feel?
Cocoa Forever.
I'm still believing.
I haven't seen any of the other retro or even modern communities try to pull off something like this. This is unique.
Next to the Switcheroo, the hottest selling cocoa product of 2018.
Episode 7 of 9. Control Break. Chuck Anders must find a way to reverse the changes to the timeline, or the entire world goes up in flames. CocoaForever.gracenote.ca.
Wow. We don't want the entire world going up in flames, do we?
No, that was David Ladd has to come and rescue it all again.
Yeah, that's it.
I have a question for you,
All right. Well, that
Bruce. How far along? Like, I'm still of that mindset that I want to pull the trigger when the whole thing's released, so I can binge the whole thing. How far away are we from having the complete series?
Well, this is number 7 of 9. Not like Star Trek, but
not a bad tie-in.
yeah. So this is episode 7. 9 is the final episode. I mean, it's.
So we're roughly 2 episodes away, right? I think he's looking for a time frame.
Time frame? Yeah. Well, what can I say? I soon. I'm chipping away at it. 8's almost ready. 9's just gonna take a little. I gotta finesse it a little bit more because it wraps everything up. So let's see, what is it? September 29 now. I would think the whole thing should be done before when's Standy Assembly? November something.
November, yeah.
I would think by Halloween, probably I should be able to have the whole thing done.
Okay, that's when I'm pulling the trigger.
Okay, awesome.
Halloween-ish.
Yeah, there we go.
There you go. Halloween-ish.
We started in springish. We might finish by fallish.
I had a quick question for you, Bruce. As you've been going through and recording it and doing everything, has the plot changed from your original guidelines a bit, or like has it adapted as you've gone through and thought of things, or has it basically been following the same script you originally came up with?
The very final piece, the final bit of dialogue has changed. Yeah, so there's been a small change at the end. As I got right up to the end, it was like, yeah, this isn't quite pulling it all together, and I got a broader view of it, the whole thing, and so I did actually change one piece at the end, but otherwise it's essentially stayed the same.
Okay, so you're going to be like a DVD and have an alternative endings version of the last episode too, with the original, or?
No, I hadn't really thought about that, but I definitely want to get everybody on the credits. I want to have a really nice credit roll, trying to list absolutely everybody who contributed. So
cool.
Maybe there'll be something after the credits.
Then we can get David Ladd in a bathrobe. If we're lucky.
Jesus!
So
there went your sales. Sorry.
Are you? No, I'm still here. No, are you going to do a T-shirt or anything, or a mug?
I could.
I think it'd be a good idea to do a T-shirt. I would definitely buy another one.
Okay. I will look into that. Thanks, Greg.
No problem.
Hey, I gotta say, episode 7. I mean, there's a couple of great guest appearances there, and Greg is one of them. You really want to check out.
Ooh, that ought to get the boost the sales right there. More Greg. Can't complain about that. All right, so from the panel, questions, comments, add-ons, thoughts about the assembly segment. We did our jump, subroutines, all that stuff. Anybody want to add
including
to that?
you, Stevie, if you have any questions?
No, I just want the pain to go.
You might have to take a break next week.
I followed it. Yeah, right now.
I was looking at my beaker image and thinking it was a live camera on your face, Stevie.
Yeah.
Yeah, I know Paul Fiscarelli was chiming in a little bit on the assembly stuff, and we had Paul on last week for our After Dark. Paul's going to start his little YouTube tutorial on assembly from the beginner's perspective.
Yeah, his first episode's up now.
I'm glad that we have...
Yep.
Yeah, oh, great. So, Paul, Paul, you are a moderator, so if you want to post a link to your YouTube channel or to your latest video, Paul, go ahead and put that in the live chat. Yeah, I'm glad that this content is out there for people. I hope it's going to spark some interest. It seems like the assembly series definitely has some interest from people. I have a number of people saying, can I get the slides? Can I get a copy of the slides and stuff like that? So I try to remind people that we will be taking these segments and editing them out into their own standalone series. So the assembly series itself will run as a standalone series. We'll just strip it out of the episodes of Coco Talk that it was in.
That sounds like a lot of work.
Not really. You just a little cut off both sides and save it as a new file. Just a little bit, not a lot. So yeah, there's more content coming. Paul Fiscarelli. Okay, so he just posted his link to his latest one, which is great. So Paul's going to have a series. We have Steve Bjork series here. I'll be starting my own assembly series, hopefully in the very near future. So hopefully as we all learn and share, and Bruce Moore, you've been doing quite a bit, right? You've been hybriding in assembly with Basic 09 and Basic and things like that.
Yeah, I've been doing a lot lately and really looking forward to these presentations to fill in the gaps. The stack is something that back in the day I had no clue about, and I'm just starting to get a clue now, so I'm really appreciating this.
Just remember, it's like being at Golden Corral. You just push a plate, you push a plate, you pull a plate,
Okay,
right?
okay.
So
You don't have those,
Just got to be careful.
Yep.
You end up with broken plates.
Simon's posted a recent video too of one of his little demos where he's playing music and animating a bunch of stuff in assembly too. So we always appreciate. What are you shaking your head for? Yes, you did. I saw it.
Yeah, it's basic. Basic.
Oh, it's in Basic.
Is that 2-layer Basic?
Yeah. Salvador Garcia says that 2019 will be the year of the 6809 assembly courses. Yeah. So yeah,
Now,
they're coming.
one thing
They're
is
coming.
that Paul and I have decided that we're going to be using the same assembler. So that
Okay.
will help a little bit when it comes to writing the code. And we're getting close to that. I think we got about 2 more lessons on the foundations of the instructions. Next week being the real biggie, which is the addressing modes. And then there's the loose end instructions, the ones that really don't fit in a category. And as far as stuff to do with interrupts and other technical hardware stuff like that, that's going to be definitely done much later in lessons, because I don't want Stevie to have too many episodes where it's DEFCON 1.
Yeah, because we already know he'll just shut the show down if it gets too.
Training.
Press the button, Frank.
Maybe I should be hosting next week then, just to make sure that doesn't happen.
We're
Not a bad idea.
Yeah, we're probably a couple weeks away from actually sitting down and writing code. And part of what I'm looking at here doing is coming up with a very basic game in assembly for Stevie basically to code. And that game will be available, the entire source code. People will be able to download it and put it on their own Coco and work along with us.
That's
so
cool.
It'll probably end up being something like Pong. And maybe the next one we do will be Breakout. But just very, very, very simple games. And eventually we'll get up to something more elaborate. But,
That's cool. That's kind of how the games in the arcade started too, like Pong being one of the earliest arcade games and Breakout. So it's kind of following video game evolution as well. So
Yep.
yeah, it was Steve Wozniak that made Breakout use only about 100 chips, where the original design was looking at 400.
wow, he was the master of cost
Yep.
reduction, right? Part reduction. So,
And people still curse some of that stuff in the Apple today.
yeah. I was going to say something. No, but I mean, honestly, we have so many people who are like this series that Steve Bjork is doing, and the fact that he's going to teach us from the ground up how to make a video game. That's so great. The fact that we have people like Simon who are making all these cool demos and showing us those source codes, and now Paul Fiscarelli, and we've had Glenn Hewlett. So many people have been doing blogs on assembly. And sharing that journey, optimizing assembly. The list goes on. I can't remember everybody's name who's done it. So the resources are out there. And I know we had that discussion, I think, last week. We would like to have more software. Being careful not to dismiss that there are people making software, so we want to acknowledge and thank those people who are making the software they are. But we always want more, right? That's our human nature. We want more software. We want more games. We want more and more and more. So hopefully this content that's being produced on helping people pick up the programming mantle might inspire and help some people get her done. And, you know, I'm looking forward to that. I don't know that I have permission to show it right now, but I'll just tell you guys, you know, John Strong has been helping me with my Cosmic Aliens game now. He's rewritten some of the ROM calls in assembly. So now not only do I have a faster P copy, I've got a faster get and put for my sprites. I've got faster fonts now too. So my game in BASIC with just these assembly routines, it is an incredibly much more faster game. It's a hard to play game now. So yeah, the assembly is real. I mean, what it can do and the speed it can provide you, it's amazing.
It's amazing.
So
seriously, you're writing a game, it's getting faster, it's requiring faster reflexes. So you're writing your own game that you can't get past level 1.
Wow.
Yes.
That's the show ended.
Yeah. And Nick Marentes, we haven't heard from you in a bit. How have you been, sir?
Oh, not too bad. Been fairly busy at work at the moment, so very little cocoa time, but I'm just prodding along on my Gunstar game slowly.
Excellent. This concludes another episode of Cocoa Talk, the world's leading live talk show featuring the Tandy Color Computer. For all things Cocoa Talk, visit us on the web at cocotalk.live. We'd love to hear from you. Send feedback, suggestions, even segments via email to cocotalk@cocotalk.live.
Cocoa Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Cocoa Talk is rocking the 8-bit world.
Consider supporting the show with a purchase of merchandise from our retro swag shop at 8bit256.com. If you'd like to become a patron of the show, click the Patreon link at our website at cocotalk.live.
Cocoa Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Cocoa Talk is rocking the 8-bit world.
Cocoa Talk would not exist without the community, its cast, crew, and contributors. Thanks go to Curtis Boyle, David Ladd, Mark Overholzer, Grant Leedy, Bruce Moore, Nick Marentes, Ron Delvaux, Rick Adams, Jason Reichert, Richard Lorbieski, Jim Brain, Tom C., Rob Inman, Mark Bosley, Brian Joyce, Ken Reichert, David O'Connor, Brian Weasler, Terry Steggy, Nick Marotta, John Strong, and many more, especially to Steve Bjork for production suggestions and James Diffendaffer for making my head explode. Please help support the Cocoa community by visiting some of its various contributors. A list of resources is available at imacoconut.com. That's imacoconut.com. The Cocoa Talk theme song is copyright 2008 by D. Bruce Moore and Greg Sheeler. Mixed, mastered, and produced by D. Bruce Moore.